instrument has ever been. It is older than most living scientists. It runs on the power of a dim nightlight, and what it is telling us is quietly rewriting what we thought we knew about the space between the stars. It was built to last 5 years. It has lasted almost 50. And what it found, and is still finding right now in 2026, was never supposed to be out there. This is the hidden story of Voyager 1. Welcome back to Proof, where we uncover the hidden truths of the cosmos. If you're new here, hit subscribe now, because what you're about to hear, most people will never know. Let me take you back to the beginning, because the beginning is where the wonder is. September 5th, 1977, a rocket lifts off from Kennedy Space Center in Florida, carrying a small spacecraft called Voyager 1. The mission plan is simple: fly past Jupiter, fly past Saturn, take some photographs, collect some measurements, then drift away into the dark and go quiet. NASA's official expected lifespan for the mission was 4 years, maybe 5. Around 1981 or 1982, the project was supposed to wind down. A successful little trip, a nice postcard from the outer solar system. Then silence. What actually happened is one of the most extraordinary things in the history of science, and most people have no idea how extraordinary it really is. Voyager 1 passed Jupiter in March of 1979 and sent back the first close-up images of that giant world human eyes had ever seen. It passed Saturn in November of 1980. Then it did something the mission brief never asked it to do. It kept going. Using the gravitational pull of each giant planet like a slingshot, it picked up speed. It picked up distance. And by the end of the 1980s, Voyager 1 had already flown farther from Earth than any object our species had ever launched into space. And it was still transmitting, still functioning on hardware that modern engineers look at and quietly shake their heads at. Drop a comment right now and tell me where you're watching from. I read everyone. Now, hold that image in your head for a second. A small spacecraft, built with 1970s electronics, powered by a lump of decaying plutonium, flying in the dark, still talking. That is already an impossible story. But this is where the real story starts. In 2012, 35 years after launch, Voyager 1 did something no human object had ever done. It crossed the heliopause. Let me explain that word, because it matters more than almost any other word in space. The sun does not just provide heat and light. It constantly breathes out a wind of charged particles in every direction. That solar wind pushes outward against the thin gas of interstellar space, where the wind finally runs out of energy and gets stopped by the pressure pressing inward from the rest of the galaxy. That is the edge of our solar system. That edge is the heliopause, a real physical boundary, the outer skin of the bubble that contains every planet, every moon, every comet, every spacecraft we have ever launched, and every living thing that has ever existed. Inside that bubble is ours. Outside that bubble is everything else. And Voyager 1 punched through the bubble wall in 2012 and kept going. It became the first human-made object in history to leave the solar system. Not a metaphor, not a technicality, a literal first, and it is still transmitting. Let me say what that means. We have, right now, today in 2026, a live instrument sitting in interstellar space, not in orbit around anything, not near the heliopause, inside the dark, cold, ancient space that lies between the stars, a space that no telescope on the ground, no satellite, no mathematical model built from a planet could ever directly observe from the inside, until Voyager 1. What it is telling us is not what anyone expected. Here's the first twist. For decades, scientists had built serious, peer-reviewed, carefully tested models of what interstellar space should look like. Those models all said basically the same thing. The space between the stars is a thin, cold, mostly quiet place. A kind of cosmic waiting room. Particles drifting slowly, not much happening. Voyager 1 walked into that waiting room and found it was a storm. Starting in 2017, the plasma wave instrument on board, a small antenna tuned to listen for vibrations in the charged gas of space, began detecting something nobody expected: a persistent, narrowband emission. A faint but constant hum in the plasma, the electrically charged gas that fills the space between stars. According to every model built to describe this environment, that hum should not have been there, not as a one-time glitch, as a continuous signal, year after year, across hundreds of millions of miles of interstellar space. A team led by Stella Ocker at Cornell University analyzed the data and published the results in May 2021 in the journal Nature Astronomy. The conclusion was very clear. Interstellar space is not the quiet, uniform place our models described. It has structure, it has texture, it has weather. It is turbulent at every scale, from distances measured in meters all the way up to distances measured in millions of miles. And we never knew, because we had never had a single instrument inside it before. Stop and let that land for a second. Every model ever built to describe the universe beyond our solar system was built from the outside looking in, from a planet, with telescopes, with math, with theory. And now the very first instrument we ever put inside interstellar space is telling us those models were missing something fundamental. The universe outside our front door is more structured, more physical, more alive than we knew. But here's the part of this story that stops being abstract and starts being personal. That same turbulent interstellar medium pressing inward is what the heliopause protects us from. The bubble, the shield. The reason cosmic radiation from distant exploded stars does not hit Earth's surface at full strength. The reason the air in your lungs still works. The reason the satellites in orbit still work. The reason we are here to talk about it. And what Voyager 1 is telling us is that the environment pressing against that shield from the outside is more energetic, more variable, more textured than any model built from Earth ever accounted for. We do not yet know exactly what that means for the long-term stability of the shield. But the fact that we now need to ask the question at all is itself a quiet shock to how we understand our own fragility as a species. Now the story gets stranger. Because before we get to what Voyager 1 found at the moment it crossed the heliopause back in 2012, we need to talk about what happened in 2023. Because in 2023, Voyager 1 almost died. For 5 months, the spacecraft kept sending a signal back to Earth. But what it was sending was gibberish, corrupted code, scrambled data that the engineers at NASA's Jet Propulsion Laboratory, after nearly 50 years of reading everything the spacecraft had ever sent, could not decode. The probe was still alive, the radio was still speaking. But whatever it was trying to say had become unreadable. The cause, when they finally tracked it down, was both simple and devastating. A single memory chip inside the spacecraft's flight data system had physically degraded after nearly half a century of constant exposure to cosmic radiation. One small piece of 1970s hardware, a sliver of silicon not much bigger than your fingernail, it had developed a fault that was corrupting the section of software responsible for formatting and transmitting scientific data. No alarm had gone off, no warning had been sent. The chip had just quietly failed after 46 years of non-stop operation, in the harshest environment any human object has ever been placed in. In any normal engineering situation, you fix a broken component by going to it and replacing it. In this situation, the component was more than 15 billion miles away, unreachable by any realistic form of transportation. No repair mission, no rescue mission. There was no way to send a wrench. The only tools available were radio signals moving at the speed of light. And even those signals took 22 hours one way to reach the spacecraft, 22 hours for a message to arrive, another 22 hours for any response to come back. A single round trip took 44 hours. Think about what that engineering loop actually looked like from inside the control room. You look at a piece of data, you form a theory about what might be wrong, you write a set of instructions designed to test that theory, you transmit them into the void. You wait 22 hours, you receive whatever the spacecraft sends back, you study the response, you learn something slightly different from what you expected. You form a new theory. You write new instructions. You transmit them. You wait another 22 hours. You do this step by patient step for months. And every single moment of that process carries the quiet knowledge that one wrong instruction, sent once across 15 billion miles, could permanently end the mission forever with no recovery possible. That is what happened in 2023. The team at JPL worked through it carefully, methodically, under a kind of pressure that almost no engineering job on Earth ever produces. And they succeeded. They figured out that the corrupted code could not be repaired, but it could be relocated. The broken section of software was split into smaller pieces, each piece stored in a different part of the spacecraft's remaining working memory, each piece individually rewritten to function correctly from its new home, then carefully reconnected to work as a whole. It was, in plain language, brain surgery, performed remotely, across a 44-hour time delay, on a machine nearly 50 years old, sitting more than 15 billion miles from the nearest human hand. In mid-2024, Voyager 1 came back online and began transmitting clean, complete, readable scientific data again. And the very first thing it resumed sending back was more of those persistent, unexplained plasma hums. The 1970 spacecraft that should have died in 1981 just kept going. And it is still going. But none of that, not the discovery, not the near-death, not the recovery, prepared anyone for what Voyager 1 had actually found at the moment it crossed the heliopause back in 2012. Because this is the part the scientific papers describe in language that starts to feel less like physics and more like something else. For decades, the models describing the heliopause predicted what crossing it should feel like to an instrument, the solar wind on the inside gradually thinning out, the interstellar medium on the outside gradually becoming detectable, a slow, smooth transition, like the place where a river slowly meets the sea. That is not what Voyager 1 found. At the boundary itself, researchers were able to identify energetic charged particles moving at significant fractions of the speed of light. Some analyses, particularly the work of researchers like Doyen Turner and colleagues at NASA Goddard, have described the boundary layer as a thick zone populated by reconnected magnetic flux. In plain words, the transition between our solar system and interstellar space is not a smooth fade. It is a sharp, energetic interface. Some scientists have described the region as a kind of wall of fire. And while that is a metaphor, it is a metaphor grounded in real measurements of particles moving at near relativistic speeds, not a poetic exaggeration. And then came the magnetic discovery. And this is the part that genuinely unsettles me, even now, when I read it. For decades, one of the foundational predictions about crossing the heliopause was that the magnetic field on one side would be clearly different from the field on the other side. Inside the bubble, the sun's magnetic field. Outside the bubble, the magnetic field of the galaxy. Two distinct personalities, neatly separated. Voyager 1 found that the magnetic fields on both sides of the boundary are not separate. They are linked in ways existing theory did not predict. The sun's magnetic field lines, carried outward by the solar wind and compressed at the boundary, were actively interacting with the galactic magnetic field. Magnetic reconnection, that's the technical term, field lines from different sources rearranging themselves and releasing energy in the process. The sun's magnetic bubble and the galaxy's magnetic field are not politely divided by the heliopause. They are exchanging energy across it, right now, continuously. That matters. Because if the relationship between our solar system and the wider interstellar environment is more dynamic, more energetic, more entangled than the textbook picture, then our picture of how the heliosphere protects Earth over long timescales needs to be quietly redrawn. Not destroyed, redrawn. Now let's talk about what is happening right now in 2026, because the story is not over. It is entering what may be its final chapter, and the timeline is tighter than most people realize. Earlier this year, on April 17th, 2026, NASA made a decision nobody on the Voyager team wanted to make. The low-energy charged particles instrument, one of Voyager 1's 10 original science packages, was switched off, not because it was broken, it was still working perfectly. It was shut down because the spacecraft is running out of power, and there was no longer enough electricity to keep it running. Voyager 1 gets its power from 3 radioisotope thermoelectric generators. Inside each one is a careful block of plutonium-238. As that plutonium decays, it produces heat. The heat is converted into electricity. At launch in 1977, those 3 generators together produced about 470 watts of power. Today, in 2026, they produce roughly 220 to 225 watts. They lose about 4 watts every year, and there's no way to recharge them. Somewhere in the early 2030s, the output will fall below the minimum level needed to run any remaining instrument at all. Voyager 1 will go permanently silent. The team has known this was coming for years. Long ago, the scientists and engineers sat together and worked out a careful plan for which instruments to shut down, in what order, to squeeze every last bit of science out of the dwindling power supply. Of the 10 instruments Voyager 1 carried when it launched, several have already been turned off. Each shutdown is one less set of questions the spacecraft will ever answer, and each one is a small funeral. But here's the twist. Almost nobody outside the JPL mission team is talking about. They have not given up. NASA engineers are currently preparing an experimental procedure that they have reportedly nicknamed internally the Big Bang. The idea is technically complex. In plain language, they are trying to restructure how the spacecraft distributes the small amount of power it still has, switching off certain onboard heaters, freeing up electrical capacity that is currently being used to keep components warm, and routing the extra wattage back to the science instruments. It sounds simple. It is not. Every change to how power flows through a nearly 50-year-old spacecraft carries real risk, and there is no manual override available, no hardware reset button, no second chance if something goes wrong. It sounds simple. It is not. Every change to how power flows through a nearly 50-year-old spacecraft carries real risk, and there is no manual override available, no hardware reset button, no second chance if something goes wrong. So the team is doing what careful engineers do. They are testing the procedure first on Voyager 2, which carries very slightly more available power, and which is a little closer to Earth, making a potential failure less catastrophic to the overall mission. Those tests were scheduled for May and June of 2026. As I am recording this in August of 2026, the Voyager 2 tests have just wrapped, and the first attempt on Voyager 1 is right at the edge of the calendar. If the procedure works, there's a real possibility that the low-energy charged particles instrument, the one that was just shut down in April, could be switched back on. The team is not making promises, but they are still trying. Because with Voyager 1, the history of assuming things were finished before they actually were has never once aged well. If hidden stories like this are why you come here, subscribe now, because we are just getting started. Now comes the moment the calendar is already counting down to. The one that is locked in. The one that no human civilization has ever reached before. On November 18th, 2026, at 14 minutes past 2 in the morning Pacific time, Voyager 1 will reach a distance of exactly 1 light day from Earth. You probably know what light speed means. The fastest anything in the universe can travel. Light moves fast enough that a beam from the sun takes about 8 minutes to reach us. That is 1 astronomical unit. A light day is 24 times longer than a light minute. A light day is the distance light covers in a full day of travel. And on that morning in November, Voyager 1 will be that far away, just over 16 billion miles, so far that a radio signal moving at the speed of light will take 24 hours to reach it. If you send a command to Voyager 1 on a Monday morning, you will not know if it arrived until Tuesday morning. You will not receive a response until Wednesday morning. 2 full days of waiting just to complete a single exchange of information. No human-made object has ever been that distant while still alive and still transmitting. And on that date, Voyager 1 will cross the 1 light day threshold for the first time, while it is still talking to us. Then it will keep going. Every hour it travels another 38,000 miles deeper into interstellar space. The communication delay will keep growing, the power supply will keep shrinking, and somewhere in the early 2030s, the last faint signal will make its final 22-plus hour journey home. There will be nothing after it. But even after Voyager 1 goes silent, the spacecraft itself will not stop. There is nothing in interstellar space to stop it. No air, no friction, no gravity strong enough to bend its path significantly. It will just keep moving in a straight line at 38,000 miles per hour into a darkness that has no end on any human timescale. And bolted to its frame is something that will outlast all of it. The Voyager Golden Record, a gold-coated copper disc. Greetings, spoken in 55 human languages. The sound of rain falling on a forest. The sound of ocean waves. 90 minutes of music chosen from cultures across the entire history of human civilization. Diagrams explaining the basic principles of our physics and our mathematics, and a pulsar map drawn from the positions of rapidly spinning dead stars, designed to show whoever finds it exactly where in the galaxy our planet sits. Carl Sagan, who helped design the record, called it a message in a bottle cast into the cosmic ocean. And that is exactly what it is. Because whoever or whatever eventually finds it, perhaps another civilization a million years from now, perhaps some form of intelligence we cannot currently imagine, the record will tell them something true, that there was a species here, that they were curious, that they built a machine from metal and electricity and mathematics, and launched it beyond everything they had ever known, carrying the sound of their own laughter. The record will still be traveling when the sun has become a red giant and swallowed the inner solar system, including Earth. It will still be traveling after every human city and every human archive and every stone we ever carved our names into has been erased by geology and time. It is the most permanent thing our civilization has ever made, and it is riding on a spacecraft that currently runs on roughly the power of a small refrigerator light. Now come back to the science, because there is one more thing Voyager 1 is doing right now that I want to put at the center of this story. The persistent plasma emission detected since 2017 is not just an oddity. According to the researchers analyzing it, it is the first continuous real-time measurement of interstellar plasma density that humanity has ever obtained. Before Voyager 1, scientists could only take isolated snapshots, brief measurements triggered by specific events like shocks from giant eruptions on the sun, traveling all the way out to the heliopause and sending ripples into the interstellar medium. Those measurements were valuable but scattered, like trying to understand what the weather is like across a whole continent by checking a single thermometer once a year in one city. What the persistent emission from Voyager 1 now provides is something closer to a continuous feed, a running portrait of interstellar plasma as the spacecraft moves through it, day after day, year after year. And what that portrait is showing us is this. The space between stars is not a static, empty background. It has texture, it has weather, it has physical structure built from charged particles and magnetic fields that stretches for hundreds of millions of miles, interacts with the outer boundary of our solar system, and changes over time. The space between stars is not empty. It is full. It is active. It has a physical personality we are only now, for the first time in human history, beginning to actually read. There's a question at the center of all of this that the scientific community has not yet been able to answer. The persistent emission has 2 possible physical explanations. The first is that the emission comes from thermally excited plasma oscillations, the natural vibration of charged particles interacting with their surroundings. That would be a genuinely significant finding, but it would fit inside existing physical frameworks without requiring them to be rebuilt. The second possibility is that what Voyager 1 is detecting is something called quasi-thermal noise, a different physical mechanism that carries information about plasma density and temperature in a subtly but importantly different way, one that would require existing models of the interstellar medium to be substantially revised. Distinguishing between those 2 explanations requires either more data from Voyager 1 itself, and it is producing less of that data every year as more instruments shut down, or a brand new mission specifically designed to study interstellar space with instruments built to settle exactly this question. No such mission currently exists. No such mission is currently funded. The earliest a follow-up probe could reach interstellar space, if it were funded and launched today, would not arrive for at least 25 years. That means when Voyager 1 finally goes silent, the question it raised will still be open. The map it started drawing will stop being updated. The only real-time window into interstellar space that our civilization has ever opened will close, and it will stay closed for a generation. That silence is coming. The date is not pinned down yet. But the direction is. Every year the power drops. Every year more instruments go offline. Every year the team at JPL makes harder and harder choices about what to keep running and what to let go. And somewhere in the early 2030s, the last instrument will reach the minimum power threshold. And the last signal will begin its long journey home, and there will be nothing after it. After that, Voyager 1 will just keep moving, silently, at 38,000 miles per hour, through regions human eyes will not reach for tens of thousands of years, carrying its golden record, continuing the journey that began on a September morning in 1977 when a group of engineers pointed a machine at the stars and pressed the launch button expecting it to last 5 years. Here is what I want you to take away from all of this. Because there is a fact sitting quietly in the middle of this story that is easy to miss when you are focused on the discoveries and the physics and the engineering. Right now in 2026, the only live scientific instrument that humanity has ever placed in interstellar space is almost 50 years old. It was built using technology that predates personal computers. It runs on less electricity than the bulb in a refrigerator. And it is sending back information that is changing how we understand the universe and our place inside it. We have built things bigger than Voyager 1. We have built things more powerful. We have spent far more money on far more complex machines. And none of those things have told us what Voyager 1 is telling us right now. Because none of those things had the one thing that Voyager 1 had. None of them had the patience to keep going long enough to actually arrive. There are questions about the universe that can only be answered from inside the universe, not from a telescope on the ground, not from a satellite in orbit, not from a mission to Mars, only from a machine that crossed the heliopause and entered the space between stars. We have exactly one such machine. It is old, it is dying, and it is running on the power of a small nightlight. As long as it is still transmitting, we need to be listening. Because when it goes quiet, the answer to some of the most important questions we have ever asked will go quiet with it, at least for a generation. The signal is still coming, stretched across more than 15 billion miles, delayed by 22 hours of travel time, carrying information about a universe that is stranger, more turbulent, more connected, and more extraordinary than any model built from Earth ever correctly described. One machine, less than a nightlight's worth of power, one chance to listen. The question is whether anyone is paying attention. Now let me leave you with the bigger meaning, because that is the part proof was built for. For most of human history, we thought the sky was a ceiling, decorations, pretty dots. Then we saw it was a clock, then a story about us. Every generation has looked up and quietly redrawn the map. Voyager 1 is the part of that story where we finally sent a piece of ourselves past the edge, past the bubble, past everything our civilization has ever called home. And what it is telling us, in its slow, faint, 48-year-old voice, is that the universe on the other side is more alive than we knew. More turbulent, more connected, more structured, more changed by our being here to study it. We are living through a quiet redrawing of the cosmic map. It is happening above our heads, in a spacecraft we built 50 years ago, while we go about our ordinary days. There is something both humbling and lovely in that even after thousands of years of looking up, the sky still has secrets we have not opened yet. That the cosmos is still calling, still whispering, still surprising the species that thought it had the map. And you just heard one of those whispers from a machine the size of a small car, on less than the power of a refrigerator bulb, older than the internet, smaller than a fridge, still talking after almost 50 years, from farther out than any human thing has ever been. Tell me in the comments, what part of Voyager 1's story surprised you the most? I genuinely want to know. Share this with someone who still looks up at the sky and wonders what is out there. And as always, thank you for exploring the hidden universe with proof.